Hello everyone, myself Prayak Patel, working as Assistant Professor in IT/ICT Department of LJ Institute of Engineering and Technology. Now in today's video lecture, I will discuss about the matching. Here in matching, we discuss also the one theorem as a false marriage theorem. Now here, see what is the matching. A matching M is a set of edges, no two of which are incident with one another. What application can you think of it? So here job assignment problem. That means job assignment to maximize efficiency. So here it is called the matching. You have to give the job to maximum number of persons, or you have to assign the job to maximum number of persons. So see here, one example is like W1, W2 and W3. Three elements available in a one set. In another set we have a 5 element P1, P2, P3, P4 and P5. Now for that we have to assign the W1 to one of the P, W2 to the one of the P and W3 to the one of the P. It is called the matching. Now another example for the matching is here in first figure. C1, C2, C3 and C4 for consider as a 4 faculties. Now S1, S2, S3, S4 and S5 consider as a 5 subjects. So here we have to assign the each subject or each faculty to one subject. So C1 assign one subject, C2 to assign one subject, C3 to assign one subject and C4 to assign one subject. So each and every faculty having a one subject. So for that we have to give the assignment or matching C match with the S. So it is called the matching. Now after that, in matching we can say that the definition or according to this figure, in figure the problem is modeled by means of a bipartite graph G equal to V. So this graph is considered as a bipartite graph because here two set C and S, where V is a partitioned as X union Y with X equal to C1, C2, C3, C4 and Y equal to S1, S2, S3, S4, S5. And the edges of G represent the here condition or relation between the two sets. So here qualification of the each teacher is given with the relation. So here C1 can teach S1, S2. C2 can teach S1, S4. C3 can teach S5. C4 can teach S2, S3 or S4. So this is a given your qualification or interested subject, and you have to assign the subject to faculty according to his interest. So here qualification or interest is given. Now for that, the age C1 S2, C2 S4, C3 S5 and C4 S3 is considered the solution for this assignment problem. That means assign the subject 2 to faculty 1, assign subject 4 to faculty 2, assign subject 5 to faculty 3 and assign subject 3 to faculty 4. Now after that, here in matching, G equal to VE be a bipartite graph with V partitioned as X union Y. So X as a first set, X1, X2, X3, X4, Y as a second set, Y1, Y2 up to Y5. Now for that, each edge of E has the form XY with X belongs to capital X and Y belongs to capital Y. What is the matching? A matching in G is a subset of E such that no two edges share a common vertex in X or Y. So no any sharing of the vertex is possible in matching. That means assign Y1 to any one of the X. Assign Y2 to any one of the X. Assign Y3 to any one of the X. In other words, we can say that a matching is a graph where each node has either 0 or 1 edges incident to it. So here degree is considered as a 0 or 1. Now after that, what is the complete matching? Now in complete matching, let G equal to V be a bipartite graph with V equal to a V partition as X union Y. Here X belongs to X and Y belongs to capital Y. Now complete matching of X into Y is a matching in G such that every X belongs to X in the end point of an edge. That means all the X can be used. So here 5 node available in the jobs and 5 node available in the candidates. So each and every candidate assign one job. So it is called the complete matching. Each and every candidate assigns some job. So it is a complete matching. Now after that, next theorem is a false marriage theorem. Now in this theorem, this figure is considered as a complete matching. So for the complete matching, we see the x1, x2, x3, x4 assign the sum value of y1, y2, y3, y4 and y5. Let G equal to VE be bipartite with V partition as X union Y. A complete matching of X into Y exists if and only if for every subset A of X, mod A less or equal to mod RA, where RA is the subset of Y consisting of those vertices each of which is adjacent to at least one vertex in A. So here A is a set of node available in your first set X. So here for node available in a X, so mod A equal to 4. Now what is RA? RA means related element of the second set with the first set. So related element of Y with the X, it is called the RA. And mod RA, that means the length of the RA. So see here, for example, if we consider A equal to x1, x2, so two element available in A, so both are subset or equal set of X. Then what is RA? So x1 having three representation or three value y1, y2 and y3. x2 having one value y2. So combination of x1 and x2 in second set as a y1, y2 and y3. So RA equal to y1, y2, y3. Now mod A equal to 2 because 2 element available in A. Mod RA equal to 3 because 3 element available in a second set. So 2 less than 3 is satisfied. That means mod A less than or equal to mod RA is satisfied according to this theorem. Now after that, here consider the first figure A as a matching. Now here not complete matching is available. So how we can check this thing? The bipartite graph showing in figure A has no complete matching. Any attempt to construct such a matching must include the x1, y1. You have to must include x1, y1 and you can include x2, y3 or x3, y3. So if you included x1, y1, then you have to try next node as I included as I is x2, y3. So if we include x2, y3, then there is no match for x3, no any possibilities for x3. Now another way, same way if you try as the next is as a x3, y3. If we include the x3, y3, then we have no find any match for the x2. So this is a problem. So we can say that this is not a complete match. Here A equal to x1, x2, x3 is a subset or equal set of X and RA equal to y1, y3 because here x1, x2, x3 connected with y1 and y. So mod A equal to 3 and mod RA equal to 2. So 3 greater than 2 condition, so it is not satisfy the theorem of the complete matching. So here we can say that this is a not complete matching, this is only matching, not as a complete matching. Now for this figure B, here complete matching is available for this figure. Now how we can represent the RA and how we can represent the mod A, what is the value of mod RA. So A as an empty set, no any element in A, then no any element in RA according to first row. So length of A and length of the RA both are 0. Now if we consider first element in A, so only x1 as A, then what is the value of RA? Connected element with x1 in second set Y as a y1, y2, y3. So x1, then y1, y2, y3. Length of A equal to 1, length of RA equal to 3. Same way for x2, y2, 1, 1. Then for the third x3, then RA equal to y2, y3, y5. Then length is 1, 3. Now for the all the combination we can consider as A and according to A we can find the RA related element of Y with respect to A. So here we can represent the all the value of A, RA, mod A and mod RA. Now for the all the value of mod A compare with mod RA, we satisfy the condition mod A less or equal to mod RA. That means here complete matching is possible. So see here, all the values are satisfied. Mode N less or equal to mode Rn. Now after that, consider this example. 5 students S1, S2, S3, S4 and S5 are member of the committee, 3 committee, C1, C2 and C3. Now we have to assign the per student one committee like this. The bipartite graph showing in figure indicates committee membership. Each committee is to select a student representative to meet with the school president. So can a selection be made in such a way that each committee has a distinct representative? So you have to find the different representative student for each and every committee. So what is the solution for that? Now for that, how we can solve this matching? How we can find the solution of this matching? For that, we have to consider this figure first. Now from the first figure, we consider the second figure, figure B. In figure B, we assign the 2 node as an extra node, one as a node A, another as a node J. Now, A means assign the value for each and every C1, C2 and C3. Now see here, we additionally add the 2 node, one A as a source and Z as a sink. Now, new edge is given capacity equal to 1. That means C1, C2 and C3, 3 are connected with the source A. And S1, S2, S3, S4 and S5, all the 5 connected with the Z. And all the new edge is weight equal to 1. That means the capacity of the new edge is A to C1, A to C2, A to C3 equal to 1. Same way S1Z, S2Z up to S5Z equal to 1. Now remaining intermediate edges, consider the capacity M. M means C1, C2, C3. 3 node is available. That means capacity of M equal to 3. So assign the capacity for each and every intermediate node equal to M. So M as a capacity and 1 is also capacity. Now see here, consider the source node as a and sink node as a Z. Now for that, one order is given. So order is like C1, C2, C3, S1, S2, S3, S4 and S5. And last node as a Z. So this is a sequence for executing this algorithm. Now for that, see here how we can find the solution, how we can find the path. So for that, we apply the algorithm as a Edmonds-Karp algorithm. So here we have to find the F augmenting path. So here first path for the F augmenting path as a P AC1, C1 S3, S3 Z. So we already know the Edmonds-Karp algorithm. So according to that, we have to assign the labeling for each and every possible node. So we have to assign label as a A1, then C1 as a A2, then C2 as a A3, then C3 as a A4, like this. Now after assigning the labeling, we find the path, first path as a AC1, means A to C1, then C1 to S3, then S3 to Z. So this is a path. Now in this path, what is the value of delta P? So delta P value is a 1 because here A to C1 capacity equal to 1 and S3 to Z capacity is also 1. So we can assign or find the delta P equal to 1. Now apply this delta P and find the flow equal to 1 because we increase the flow by 1 because delta P equal to 1. Now second time when we apply this algorithm, then we will get the another path. So if here we increase the value by 1, that means in figure B, we see that capacity and flow as a like A to C1 as a 1, 1, C1 to S3 as a M1 because M as a capacity, 1 as a flow, and S3 to Z as a 1, 1, 1 capacity and 1 flow. So this A to C1 and S3 to Z is considered as a block line. Now after that, consider the another way or another sequence. Now here see that another sequence as a, here already we select the one relation C1 to S3. That means C1 committee assigned to the student S3. Now after that, find the second path according to same method. So here we find the another path as a A to C2, then C2 S1, then S1 Z. That means here we consider this path and in this path we increase the capacity by 1 because here delta P value equal to 1 for these three ages. So here we increase the capacity by 1 and we select the one another age as a C2S1. That means committee 2 assigned to student S1. Now after that assign the third relation or third capacity or third path as a AC3, C3S2 and S2Z. Now increase the capacity by 1 for this path because in this path capacity and flow difference equal to 1. So here we increase the capacity by 1 and we select the another path as a C3S2. That means student 2 assigned to committee 3. So here we can say that the final solution for this 3 committee with the 5 students as a S1, C1, S3. That means committee 1 assigned to student 3. Second solution C2, S1. That means committee 2 assigned to student 1. And C3, S2. That means committee 3 assigned to student 2. So this is a solution for this example. Here we discuss about the how we can find the matching in our algorithm. So in this video we discuss this point. Thank you for watching this video.